Good afternoon. This is the Chem 101 second hour exam review. I'm going to go over select problems on the exam that I saw many people miss. The first problem I would like to go over is problem number 6. 3.65 moles of titanium contains how many atoms? You remember from Avogadro, 1 mole is equal to 6.022 times 10 to the 23 atoms of any element. So 1 mole of titanium is 6.022 times 10 to the 23rd atoms of titanium. We have 3.65 moles, so 3.65 moles Ti over 1 times 1 mole Ti, 6.022 times 10 to the 23rd atoms Ti, so it's 3.65 times 6.022. The answer is E, 2.2 times 10 to the 24th. Number 8, in the reaction of, where's the eraser gone? In the reaction of 2 moles of, let me see, take that out because that is no longer true. In the reaction of 2 moles of ethane with 7 moles of oxygen to give 4 moles of CO2 and 6 moles of water, increasing the concentration of C2H6 at equilibrium will what? It doesn't change the activation energy, just simply because we are not changing the identity of a reaction or a product. The activation energy is that amount of energy it takes for your starting material to get to the very top such that bonds, let me draw it over here. The activation energy, E sub A, is the energy that it takes to get from the starting material to an intermediate, a transition species, where it's not really starting material, it's something else, but it's not yet product. Bonds are beginning to break and bonds are beginning to form. New bonds are beginning to form, old bonds are beginning to break. So the energy that it takes to get there is called the activation energy. If you change the concentration of your starting material, it doesn't change, since you're not changing the identity of the starting material or the product. That activation energy is going to be the same. Increasing the concentration of that isn't going to change the reaction. How much you have of this is not going to determine how fast the reaction occurs. That's totally different. So the correct answer here is none of the above. Let's look at number 13. If the initial pressure of a system was 1 atm, the volume was halved, and the Kelvin temperature was tripled, what is the final pressure? Do we have moles? No, so we can't use Pivnert. Do we have pressure? Do we have only pressure? No, we've got pressure, temperature, and volume. So we have combined P1 V1 over T1 is equal to P2 V2 over T2. If the initial pressure was 1 atm, so our P1 is 1 atm. The volume halved. Well, since we're not told what the volume were, the volume did change. So we have a V1. Set our V1 to any value that you want. let's just say it's 100. Let's say it's 100 ml. If V1 was halved, it was cut in half, V2 is 50 ml. If the temperature was tripled, it's asking what the final P2 pressure is. So we don't know what the initial temperature was, but whatever change was made, it was tripled. Let's say your T1 is 273 Kelvin. Let's say it's 100 Kelvin. Let's say your initial temperature was 100. It didn't say what the temperature was. It just said from its initial value, it was changed to 3 times that. If T1 is 100, T2, if it was tripled, is 300 K. Solving for P2, we need to multiply by T2 over V2. T2 drops out, V2 drops out. Whatever we do to one side, we got to do to the other. T2 times V2. So P2 is equal to T2, P1, V1 over V2, T1. Are the temperatures in Kelvin? Yes. We have units of volume, we have units of pressure, okay? So P2 is equal to T2, which is 300 Kelvin, P1, 1 atm, V1, 100 ml, divided by V2, which is 50, T1, 100 K. Let's look at our units. K above, K below, ml below, ml above. What units are we left with? ATM. What units were we asked to calculate for? Pressure, ATM. Are we in units of pressure? Yes. So we have 300 times 100 divided by 50 divided by 100. So the 100s cancel. So it's 300 divided by 50, 6 ATM. Let me see. Number 19. Which following ionic compound is soluble in water? Here, you're looking at the cation and the anion, starting on your first chart of your solubility chart. Of these, aluminum nitrate, NO3, is in that very first box on the compounds that are mostly soluble. If you have nitrate paired with anything, it's soluble. You don't have to worry about it. So nitrate here, B, is the correct answer. All the others, if you look at either phosphate and you look at what it's paired with, it is insoluble. Sulfate, when paired with barium, is insoluble. Hydroxide, when it's paired with magnesium, is insoluble. Sulfate, when paired with lead, is insoluble. So the correct answer here is B. Number 22, a solution is made by mixing 569 ml of water and 409 ml of ethanol. What is the concentration of ethanol in units of volume, percent? So volume, percent is equal to volume of solute divided by volume of solution times 100. If I use the other expression, part over whole, the part here is your solute, what's being dissolved in the solvent. That's our part. Our whole is the solution. Which liquid is present in the lesser amount? We've got 569 ml of water, but 409 ml of ethanol. So ethanol is the solute. So we have 409 ml divided by the total solution is the ethanol and the water. So it's 569 plus 409. 1817. So this is 978 times 100. This is 41.8%. Answer A. We see 22. Let's look at 26. It took 42.35 ml of H2SO4 to neutralize 21.17 ml of 5.5 molar sodium hydroxide. Calculate the concentration of H2SO4. First thing you do is write the reaction. Sodium hydroxide, base, reacts with the acid H2SO4, produces water, H and OH. H2O is H and OH. There's H, there's OH. What's left over? Sodium sulfate, Na2SO4. Question: the way that the reaction is written, is it balanced? Na, OH, H, and SO4. We have OH, H, and A, SO4. Do we have the same kinds of things on both sides? Yes. Next thing, 1 in front of everything. 1, 1, 1, 1. 1 Na, 1 OH. 1 H2SO4, but there's 2 H's. 2 there, 1 there. We have 1 sodium sulfate, but there is a 2 following the sodium. So it is 2 Na. Water is HOH, 1 OH, 1 H. We have 1 sulfate. Right now, we're not balanced. Let's take it to the most complicated thing is the sulfates. Balanced. Next most complicated thing, the OH. 1 there, 1 there. Two sodiums, 1 sodium. So what does that mean? We've got 2 sodiums here. We need to have 2 sodiums on the other side. We can't change the subscript because that changes the compound. Na2OH does not exist. So we have to put a coefficient of 2 in front of that. Makes 2 Na, it makes 2 OH. So we've got our sodiums balanced, our sulfates are balanced, but notice our H and OH are not balanced. So this is 1 OH, 1 H, we need 2. So we put a coefficient of 2 in front of that. Now we have 2 OH and 2 H. Now the equation is balanced. We have the same kinds of things on both sides. We got the same numbers of things on both sides. From this equation, it says 2 of these react with 1 of those. What kind of equation is this? This is a molecular reaction. Every compound that's listed, reactant and product, are in terms of moles. So this equation says 2 moles NaOH equal 1 mole H2SO4. This is an equality. As I shout in class, any equality can be creating two fractional friends. So we have 2 moles NaOH per 1 mole H2SO4, or 1 mole H2SO4 for 2 moles NaOH. From our equation, we know that we have 42.35 ml of our sulfuric acid solution. We know from our NaOH it was 0.500 molar, and we had 21.17 ml of it. Well, what does that mean? Well, what are we asked to calculate information about? That guy right there. So we're going to have to end here with this guy, H2SO4. So where's the only other place that we have information about that we can work with? Right here, your NaOH. So this is where we start. This is where we end, because this is what it's asking for. It's asking for information about H2SO4. So we have 21.17 ml of a 0.500 molar NaOH solution. Well, kind of like that, But what other information about the sodium hydroxide do we have? We've taken care of that. What other information about the NaOH do we have? We have that it is 0.5 molar. But what does molarity mean? It equals moles per liter of solution. So if it's 0.5 molar, we have 0.5 moles NaOH per 1 liter of NaOH solution. Okay, that's what molarity means. But do we have 1 liter of NaOH? No. We only have we only have 21.17 of NaOH. So this is in ml, we need to convert it to liters. Divide by 1,000. So this is 0.0217, 117 liters of a 0.5 molar H2S sodium hydroxide solution. So we've used that bit of information. Where does that leave us? Well, let's look at our units. Liters cancel. We are left with units of moles. This is moles about NaOH. But where do we want to go to? We want to go to information about the sulfuric acid. Well, do we have any information up here that talks about and relates moles of sodium hydroxide and moles of H2SO4? That guy right there. We can create two fractional friends. So we want that form that starts at moles of NaOH and ends up at H2SO4. So we have 2 moles NaOH, 1 mole H2SO4. Moles NaOH cancel. What units are we left with? Moles of H2SO4. Okay, what is it asking for? It's asking for what is the molarity of H2SO4. Again, what's the definition of molarity? Moles per liter. Well, we need a volume term of H2SO4. Do we have a volume term? Yeah, we do. We have 42.35 ml of our sulfuric acid solution. So all we need is moles of our sulfuric acid, and we're done. Because if we have moles of H2SO4, we know that that many number of moles was contained in 42.35 ml. So right now, we're basically done. What is the... So we need to calculate this number of moles of H2SO4. Let's say this is Q. Q number of moles of H2SO4 was contained in not 42.35 liters, but 42.35 ml. So we convert that to liters, we put it down there, we should be able to get to our molarity. Remember, the units we're here in right now is moles of sulfuric acid. We're on 26. It's wanting molarity, which is moles of H2SO4 over the total volume of solution. Total volume of solution was 42.35. Change that to liters. 0.04235. The answer turns out to be 0.1250. That was 26. Seven, 28, and that's it. Okay. Let's look at 27. Consider a solution which is 0.1 molar in acetic acid and 0.2 molar in the sodium acetate. So we have a buffer that is a combination of a weak acid and the conjugate base. What is the purpose of a buffer? A buffer is present to control the pH of the solution. That if you were to add acid or base to it, the pH does not change radically. That's the purpose of a buffer. A buffer is made up of the weak acid and its conjugate base. Correct. It says, which of the following statements is true? A small amount of sodium hydroxide, the pH decreases, gets numerically smaller very slightly. If the pH goes from, let's say, we have a pH of 6 and it changes to 5.8, we are going more acidic. When you add a base to a solution, do you go more acidic? No, you go more basic. Your pH will get larger. pH 6, maybe to 6.3 or 6.4. So it's not A. If the sodium hydroxide is added, the OH minus reacts with the acetate anions. Well, no, this is a base and that is a base. If you have an acid and a base, the acid reacts with the base. The OH minus is our added base. Does it react with the acetate anion? No, it reacts with the acetic acid. D, so it's not B. Let's look at D. If HCl is added, the H plus that's generated from the acid reacts with the acetic acid ions. Well, first off, this is not an ion. This is a neutral compound. This does not have any place to pick up a hydrogen. This is an acid. It wants to donate the hydrogen from this guy. So we have H plus reacting with something that wants to create H plus itself? No. E, if more acetic acid is added, the pH increases. Okay? Our pH is starting out at 6. If we add an acid, means making it more acidic, it means the pH should go down to 5.8, something like that. But does our pH increase? No. Answer C. If a small amount of HCl is added, the pH decreases, gets numerically smaller. So we're adding a strong acid to our buffer. We're adding a strong acid. It reacts with the base. So the pH is going to change from 6 down to 5.8. We're decreasing some of the base that's present. We're making it more acidic. 28. No, that was 27. 28. Which solution is the most acidic? Most acidic. The pH numerical value of 7 is lower than 7. So which of these has a pH value that is the smallest? Well, we can eliminate some of these right immediately. We can see the exponents on these guys. When we do the logarithmic operation, whoops. When we do the logarithmic operation, usually if this first number is not 1, like 1.0, it is 1 less than 8. So this is a pH of about 7 point something. Is approximately 7 point something. If the first value of the first value is exactly 1.0, and you do the log base 10 of it, the exponent drops down and becomes the first value. So your pH here is exactly 7. Here, we have 1.9 times 10 to the minus 8. Since this is not 1.0, we do this mathematical logarithmic operation, it is 1 less than this. So the pH here is about 7 point something something. You don't know what those, I don't know what those two numbers are right off the bow, but we got pHs of 7. We have two values here that are much larger than these guys. So it's going to be either E or C. If we do the logarithmic value, log base 10 of 1.0 times 10 to the minus 2, the pH here is exactly 2.0. 2.00. Since this is not 1.0, there is some other value here, we subtract 1 from this. So the pH here is 1 point, I think it's 7 or 1.8. So answer C is the most acidic solution. Those were the problems that I saw on the exam that were most commonly missed. Please, if I did not cover a problem that you wanted covered or you need more explanation, please make an appointment to come to my office hours and we'll get this taken care of. Thank you very much. Have a good day.